Hello my shimmering stars, today I Shaurya Grover welcome you all to this amazing platform of PW Gulf. So my Gulf students, I welcome you all to your Achievers batch. And what are we going to do today, ma'am? Today we are going to start with our new chapter, that is classification of elements and the periodic properties. So I guess you all are ready for this wonderful session of ours? Yes. How we are going to cover, what are we going to do? See students, basically this is going to be the ultimate recap session. That means we are going to complete the whole chapter in this particular session. Now the name itself says ultimate recap. That means we have to do the revision. Yeah, recap in other terms is revision. So how are we going to proceed? Can you tell us, ma'am, that what are the important topics from which questions are asked? Don't worry, we'll come one by one on that part as well. So before starting the students, there are few lines for you all. Do remember this always. Passion is the fuel that ignites the fire of hard work, turning dreams into reality. So students, you should have passion in whatsoever, you want to do in life. Whatsoever work you do, whatsoever thing you are going through, or you are in a particular phase, you are preparing for a certain examination, you should have a passion for that. That yes, I have to learn something. Don't always think that yes, I have to, become a topper or I have to bring good marks. No, don't think about it. Think that you have to learn something. When you keep this in your mind, you are going to progress. Yes? So now students, let us turn your dreams into reality. That means if you want to do that, you need to do hard work and smart work. For that, we shall start a session. Yes. So students, as I've already told you, we are going to start with classification of elements and the periodic properties under your ultimate, recap session, ultimate recap session for your Achievers batch. Yes, students, are you ready for all of these? Let me tell you. First of all, I shall be showing you that what are the topics we are going to cover. And then I will be letting you know that yes, these topics you have to do first. Then you have to do this topic at the second number and then the third one. So that, as per the demand of the question paper in your competitive examination, we have to study smartly. Yes. So students, moving on to the, today's target. So basically, as you all know, it is ultimate recap, though we are going to complete each and every topic. We are not going to leave any of the topic over here. We will be covering each and every topic. So we shall be starting with the very first segment, that is going to be Daubernier's trade. Right? From where does the classification started? Initially, it was Daubernier who started. So Daubernier's trade we are going to start with. Then we shall be proceeding towards the Newland's law of octave. The next segment, students, that we will be covering will be about Luther-Meier's curve. Yet again, very interesting part in Luther-Meier's curve. You are going to see a graph between atomic weight, atomic volume. So you are going to understand that where elements are kept. Very interesting part. Moving on to the next part, we have Mendeleev's periodic table, and then comes the most important, that is modern form of periodic table. The table that we do have at our homes, the table that is pasted on the cupboard. Yes, everybody, if you are a chemistry aspirant, if you are a chemistry student, you very well know the importance of periodic table in your life. The whole inorganic chemistry revolves around it. Yeah. The next part that we are going to do is going to be the nomenclature session. Now, nomenclature here we are going to cover for the elements whose atomic number is more than 100. I will let you know that if you have a digit 1, what you have to use. If you have a digit 2 over there, what you have to use. In a similar way, for example, if I'll ask you do the nomenclature for 114th element. So you should know that for 1 you have to use this word. For 4 you have to use this word. In this way you are going to do the nomenclature. Moving on to the next part, students, we shall be starting with classification of elements. Now, classification of elements as in, ma'am, basically we are going to classify elements as S block elements, P block, the D block, the F block ones. In this way, we are going to classify the elements. For the students, we are going to do the periodic properties. Now, over here in the periodic properties, we are going to deal with atomic radii, ionization enthalpy, and furthermore topics are electron affinity or electron gain enthalpy and electronegativity. So, these are the periodic properties that we have to focus upon. Now, see students, periodic properties is not the end. You just not need to understand them, but also you have to cover the variation segment. The most important part is variation in the periodic properties. Ma'am, what do you refer to the term variation? What it is exactly? See, in the periodic table, if you look upon, I will be providing you in the question paper. If you scroll up the question paper, the previous year ones, you shall be observing that there are some questions. For example, they have given you 4-5 elements, okay, and they ask you to write the trend for the atomic size, increasing order of atomic size, or they would ask you to write the trend for decreasing electron affinity. So how you are going to answer that? What is this basically? What is this trend word? That it is increasing, it is decreasing, this element has largest, this element has smallest. Okay. For example, let us talk about, if I'll ask you in many of the question papers, these two questions are so common, that which is the most electronegative element in the whole periodic table? Which has the highest electron affinity among the whole periodic table? So if I'll talk about the most electronegative element, that is fluorine. If I'll talk about the highest electron affinity holding element, that is chlorine. So these kinds of questions, how we are going to solve? By the variation part. Yes. So these are really very important. Over here I have mentioned periodic properties such as atomic radii, ionization energy, electron affinity, electronegativity, along with their trends. Also with their trends, that means the variation parts we have to cover, because that is really very important. And do you remember a word exception in chemistry? So that exceptions we are going to observe in the trends segment. Yes, everybody. Now I'm going to come to the part that where you need to do the smart work. Though I will be explaining you each and every segment of this particular chapter, each and every segment we are going to cover for this particular chapter, but yes, I want you all to know at least that from which maximum questions are asked. That means I will be showing you over here that these topics are the one which are, the ones from which maximum questions have been asked till now. Till now, okay. We have seen from so many years, okay, we have observed this, and as per the data that we have analyzed, we got to know that maximum questions are asked from the topic periodic trends in properties of the element. Okay. So this is what I was saying, the variation segment, the trend segment is really very important. So this is basically based upon the part that which holds maximum number of questions to this topic. And then comes electronic configuration. Then comes the electronic configuration, and the next one is modern periodic law and nomenclature of elements. Clear, everyone? So these are the segments from which maximum questions are being asked. Now starting with the introduction section of R, as I've already told you what is the today's target. So we are going to start with the introduction, that means with the Daubernier's trade. So basically student, Daubernet was a scientist which introduced law of trades. Okay, so we are going to start with the periodic classification. We initially start with Daubernier's trade. Now, as per Daubernier, he introduced law of trade. Now, what is the meaning of the word trade, ma'am? Trade word is basically referred for 3 elements, a group of 3 elements. A group of 3 elements is a word trade used for. Now see, he arranged similar elements in a group of 3 elements called trades. 3 trades. Now what he was doing, why he took 3 elements? Because he told that the atomic weight of the middle element is basically the sum of, the average sum of first and third element. How is it possible, ma'am? How it is possible? He took an example of lithium, sodium and potassium. He took their example, and while he took their example, he told that the atomic weight of sodium comes out to be sum of atomic weight of lithium and potassium by 2. Average atomic weight by the first and the third element. So see, according to him, atomic mass of the central element was merely the arithmetic mean of the atomic weight of the other 2 elements over there. So this was basically the law of trade. Students, I would request each and everybody of you to mention and write down each and every characteristic over here. Each and every characteristic over here. Now see, these are the atomic weight that I have mentioned. This is the value of A over here. This is the value of A over here. This is the value of A over here. Atomic weight is represented by capital A. In other terms, it is atomic mass. So for sodium, if I have to calculate, it comes out to the sum of 7 plus 39 by 2. That is 46 by 2. That comes out to be 23. So it comes out to be similar to that of provided one. Calculated and experimental came out to be same. That means it exhibits that the whole trades law, the law of trades, is based upon which concept? Atomic mass concept. So it is based on atomic mass. Upon what? Atomic mass. Very simple thing. Very simple thing. It is based upon what? Atomic mass. And do remember this given principle, that atomic mass of the central one, that means of the second element, comes out to be the arithmetic mean of the atomic weight of the first and the third element. Clear? Now students, with regard to this, he created a table in such sort of way, where lithium, sodium, potassium we have already done. Similarly, he gave some examples of calcium, strontium and barium. If you are going to calculate for strontium, it is going to be arithmetic mean of the first and the third one, 40 plus 137 by 2. Approximately it came out to be 88. Then similarly for chlorine, bromine and iodine, he did the same way. He calculated for bromine, it approximately came out to be 80. It was exactly 81 point something, but it is close to 80, so that it follows the Daubonier's trade. That means the law of trades over here. But yes, there were some exceptions. There were some exceptions. That why it failed out, students. It failed out. Let me tell you what were the exceptions. For example, in the same group, this law is not followed. For example, we know that group number 17 holds fluorine, chlorine, bromine, iodine. Yes, everyone. Chlorine, bromine, iodine follows this law, but fluorine, chlorine, bromine does not follows this. That means in the same group, fluorine, chlorine, bromine, iodine, that are the halogen family, here the initial 3 are not following the law, but next 3 are following the law. So yes, it is not valid for all the elements. Clear, everyone? So this is a different thing. And also all the non-elements were not placed as per this law. So this is again a limitation for the Daubonier's trade. Now moving on to the next one, we have Newland law of octaves. Newland law of octaves. Now Newland, when came into account, he just introduced through with the help of musical notes. Now I don't know you love music or not, but I do so. So have you heard the sargam? Sa re ga ma pa dha ni sa. I'm starting from sa, ending at sa. Now count it. Sa re ga ma pa dha ni sa. How much? Starting from sa, ending at which note, students? 8th. First and 8th are showing the same properties, sa and sa. Okay, so if you see sa re ga ma pa dha ni sa. Starting again. Sa re ga ma pa dha ni sa. So first and 8th element are showing the same property, sa sa, just as the musical notes. Clear? I don't know my voice was as much as beautiful or not. Okay. And so coming back to this topic, Newland of octave. So octave here refers to as that first element will show, first element will exhibit the same property as that of 8th element. So this is Newland law of octave. Now this is basically till calcium only. So there are some exceptions right again here also. Moving on to the next one, that comes Mendeleev's periodic table. Yeah. So coming to Mendeleev periodic table, before that we have one more, that is the Luther's Mayer curve. So I'll just mention it over here only. Let me take a blank slide for this as well. Yeah, so here we also had one more, that was about Luther-Mayer's curve. Before Mendeleev, we have Luther-Mayer curve also. Now see, till now we have studied that all of these laws again are based on what? They are again based upon atomic mass. Based upon atomic mass. Coming to the next one, Luther-Mayer curve. Now see, he plotted a graph. What he did? He plotted a graph between atomic weight and atomic volume. What we observed? This was seen. Such kind of graph was observed. Now, as per such kind of graph, here we have these peak position. The peak position, students, represent the alkali metals. All the alkali metals were placed on the peak position. Then, all the bottom position, that was holded by D block or the transition elements. D block or the transition elements. Then comes the ascending position. This is ascending. This is ascending. This is ascending. This is ascending. So, ascending positions were given to halogens. Ascending position were given to halogens. Now comes what? Descending position, descending position, descending position, descending position, descending one. Descending position were allotted to whom? Ma'am, descending positions were allotted to alkaline earth metals. It were given to alkaline earth metals. Everybody, first of all, draw this graph. Everybody do this. Everybody please do this. Also, one more thing I told you, this is based upon atomic volume and atomic weight. So, this is Luther-Mayer's curve. This is Luther-Mayer curve, everybody. Please draw this so that we can move on to the next part now. Yes. Now come Mendeleev into account. Again, this law was also based upon the atomic mass. Coming to Mendeleev, Mendeleev basically focused and he discovered so many elements. He also discovered some elements which were not discovered at that spot of time. So, he basically predicted that there will be some elements which will be present at a certain position. So, basically how he did, he divided the periodic table into 7 horizontal rows, which is referred to as your periods, and 8 vertical columns, that is groups. So what he did exactly, he said that periodic table is now divided into 7 horizontal rows, which is periods, and 8 vertical columns, that is groups. So, groups, that means from top to bottom, periods, that means from left to right horizontally. Now, and each group students is further subdivided. For example, 1A, 1B, in such a way. Each group is further subdivided. Group A basically represents normal elements. Group B basically represents the transition elements. Clear, everyone? Now, 8th group is not yet subdivided in this particular part. 8th group was not subdivided. Group 1st to group 7th were divided into 1A, 1B, 2nd A, 2nd B, 3rd A, 3rd B. and so on. 8th was not subdivided. Now, by this way he predicted it. Okay, the periodic table, he placed the periodic table. Now see, here you can see that here gallium is written, here germanium is written. Yes, so he said that he initially did not discover these elements. He just that 2 unknown elements he named it. He said that Eka aluminium is present and Eka silicon is present. Eka over here refers to as that one element will be discovered after aluminium, one will be discovered after silicon. So he left an empty space. He left an empty space and named these elements as Eka aluminium and Eka silicon. So basically he predicted these elements. And in future students, Eka aluminium is basically gallium and Eka silicon basically is germanium. It is basically germanium. Clear everyone? So this in future came into account that yes, there were some elements that are present below aluminium, below silicon, and which came out to be known as gallium and germanium, which exhibits the same properties as that of Eka aluminium and Eka silicon. The same kind of properties, same kind of properties. Moving on to the next part, what are the merits of Mendeleev's periodic table? Initial merit is element with same properties were placed in same group. How come? How come they are placed in same group? See, for example, I guess this also answers the question that why there is a need of periodic table as well. For example, you go into a school, okay, and there are so many students with different, which belong to different classes. Class 1st, class 2nd, class 5th, 6th, 10th, 11th, 12th and so on. And you are the one, I go there and I ask you that, please kindly call that particular student. Now, you don't know to which class that students belong. How you will know? For that, what you are going to do is, you are going to assemble them all together. Class 1st students come over here, 2nd over here, 3rd over here, 4th over here. So that assembling of all the elements as per their properties is periodic table, is periodic classification. So what he did, that a particular class holds similarities such as age group, such as intelligence. A particular class hold the same similarities. You cannot, make class 1st student to sit in class 12th. They have a difference in the age, in their intellect. So basically this is what I am saying is elements with same properties were placed in same group. Next part. It is easy to predict the properties of unknown elements of which gaps were left, Eka aluminium, Eka silicon. Next part is he made collective study of elements possible. Now you can study a lot of elements all together, right? Because some of them holds the same characteristic. He left gaps for the undiscovered element already discussed. Next. Demerits. What were the demerits, ma'am? Grouping of dissimilar elements. What he did, he placed first A and first B all together. First A and first B elements had dissimilar properties. They don't match each other, but they were kept in first A and first B respectively. First A elements and first B elements don't have same properties but were kept together. So this is one of the demerit. Another, separation of similar elements. For example, platinum and gold. They were separated. They had some kind of similar properties, but they were separated out. Isotopes. Now he said, according to Mendeleev, elements are placed as per increasing atomic mass. Yes, but in the case of isotopes, let us consider of hydrogen only. Atomic number 1, 1 and different atomic mass. What is isotope? The one which have the same atomic number but different atomic mass. Now, all of them have different mass, but they were placed in the same category. Why? They should have been placed at different positions. So that means this does not follow the Mendeleev periodic table. The next one, anomalous pairs. Next demerit. Cobalt has atomic weight more than nickel. It should be placed after nickel, but nickel is placed after cobalt. You have to place them according to increasing atomic mass, but over here the scenario is different. Cobalt, which has higher weight, should be placed after nickel, but nickel is kept after cobalt. So this is again one more demerit. The last demerit is position of hydrogen. See, hydrogen possesses some characteristics of group number 1st and some characteristics of group number 17th. Group number 7th. So it was a confusion fundamentally to place it at first, you know, in first group or in group 7th. So its position was uncertain. So this is again a demerit. Clear everyone? Now student, come into account Moseley's law. Moseley basically helped to attain, you know, the periodic classification because his law was based upon atomic number. Till now we were focusing on atomic mass, but now we are going to focus upon atomic number. See, now let me tell you first of all the experiment. See, in the experiment he took, you know, a box of a metal or a substance and he bombarded some X-rays. Now that X-ray basically had some frequency. So he observed that root of frequency is directly proportional to the atomic number. That means when he is plotting a graph of the root of frequency at atomic number, he is getting a straight line. But when he is plotting a graph of root of frequency and atomic mass, the line is not straight. That means it is not dependent upon atomic mass, it is dependent upon atomic number. So as per the Moseley law, Moseley studied the frequency of X-ray produced by the bombardment of a strong beam of electron on the metal target. Okay, now he found that square root of frequency of X-rays is directly proportional to the number of effective nuclear charge. What is effective nuclear charge? It is Z. What is effective nuclear charge? Z or the atomic number. But not to the mass number or the atomic mass. Till now we were saying that periodic classification, we are classifying elements on the basis of the atomic mass, but it is not true, students. It is dependent upon atomic number. Clear? Now, clear everybody? That's great. This was given by Moseley. Now comes the periodic table of elements, students. So this is your periodic table. How the periodic table is being classified, let us understand this in depth. See, these two groups, group 1 and group 2 are, this is group 1, this is group number 2. These two are S block elements. Why they are S block elements? Because the last electron enters into the S subshell. Now, from group number 13 to group number 18, see group 13, 14, 15, 16, 17, 18. From these group, all of them, students, are your P block elements. Why are the P block elements? Because the last electron enters into the P subshell. Let us talk about the D block elements. From group number 3rd, to group number 12 are D block elements, because here the last electron enters into D subshell. Now what about S block elements? See, here you can see that from 50, here is 57th element, okay, which is lanthanum. After 57, the element is 72. Element has atomic number 72. Over here, it is 89. Over here, it is 89. And after 89, atomic number is 104. So where are these inner elements? From 58 to 71, from 90 to 103. These elements are placed under which group? Under which family? These are F block elements. Which elements? F block elements. Because here the last electron enters into F subshell. So they are kept separate. They are taken out and kept at below position. Clear? Do remember this. This is a very new thing over here that you should know. You should know. Clear? How are these placed? Let us discuss. See. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. In such a way, they are placed. Let me tell you, this is group 1 elements, which is alkali metals. Group 2, alkaline earth metals. This 13th group is boron family. Carbon family, group 14. 15 group nitrogen family. 16 group oxygen family. 17 group halogen family, and 18 group the inert gases. Done, done, done. Yes, everybody, tell me fast. Clear, everyone? Now come the magic numbers. What are magic numbers? What are magic number? Magic number is basically how to calculate the atomic number of elements. So for group 1 and group number 18, magic number is 2, 8, 8, 18, 18, 32. See over here. For example, you know the atomic number of hydrogen as 1. Add 2 into it, you will get 3. Add 8 into it. Sorry. Add 8 into it, what you will get? Na. Add then again 8 into it, 19. Then add 18, 37. 18, 55. Then add 32, 87. So 2, 8, 8, 18, 18, 32. For group number 1st and for group number 18th. Add 2, add 8, 8, 18, 18, 32. You will get the atomic number of all the elements in such a way. This is for group number 1st and 18. Now for the next one, if you will see, for group number 2nd and from 13th to 17th, group number 17 and 13th to 17th, it is going to be 8, 8, 18, 18, 32. Don't add 2. Start from 8, 8, 18, 18, 32. Let me tell you one more thing. Over here, these are groups. Group number 1 and so on, right? These are periods. Horizontal one. First period, second period, third period, fourth period, fifth period, sixth period, seventh period. Sixth period, seventh period, because they came over here, right? Clear? Now students, come the nomenclature. Nomenclature with atomic number who has more than 100. How you have to do? For example, you have been given 101. For 1, you have to use un. For 0, you are using what? Nil. For 1, what you are using again? Un. And at last, very, very important, you have to add em in all. What you will obtain the name? Un, nil, un, em. How you have to represent? The initial letters. U, N, U. Clear? Let me tell you for which number what you have to use. For 0, you will be using nil and you will represent from the initial letter, that is N. For 1, you will use un, initial letter you will use U. For 2, you will use bi, initial letter you will use B. For 3, you will use tri, initial letter you will use T. For 4, you will use quad, initial letter will be Q. For 5, you will use pent, initial letter will be P. For 6, you will use hex, initial letter will be H. For 7, you will use sept, initial letter will be S. For 8, you will use O, initial letter, and oct. For 9, if you don't know, it is E double N, and initial letter will be E. Clear? Clear everyone? So by this we have to name, write the numbers and at the last EM. Clear everybody? This was about nomenclature and these is about nomenclature. They have also provided their real name. So for the real name they have written for 001 it is Mendelium, Nobelium, Laurentium, Ruthenium. Okay, so these are the names also that are official names. Clear? And these were the names of the nomenclature. Moving on to the next one now, prediction of period, group and block. How you are going to, predict to which period does it belong, to which group or to which, block it belongs. See, for S block, if you have to calculate group number, for S block elements, group number is equivalent to number of valence electrons. So, valence electrons are the electrons that are present in the outermost shell. So, that will define you for S block elements. Now, for P block elements, how you have to calculate 10 plus number of valence electrons. Okay, 10 plus number of valence electrons. For example, group number 13th. Okay, in group number 13, boron family. Let us talk about boron. How many electrons are there in the valence shell? 1s2, 2s2, 2p1, 2s2, 2p1, 3 electrons. So 10 plus 3, 13. That means it belongs to 13th group in such a way. For D block elements, what you have to do, group number if you have to calculate, number of electrons in n minus 1 d subshell plus number of valence electrons. Clear? So this is for the group number. For period, how you have to see? For period, see number of shells. That means check out the value of n. Small n. N now you know you have done in the second chapter, principal quantum number. So if you know the value of n students, you can clearly tell me which period does it belong. And how you have to see block? How you will check block? If last electron enters into S subshell, it will be S block. If last electron enters into P subshell, it will be P block. If last electron enters into D subshell, it will be D block. Clear everyone? That's great. That's great. That's superb. Now let us talk about metals, non-metals and metalloids over here. Now these lines are from the NCERT. These lines are from the NCERT, everybody, about metals, non-metals and metalloids, because I want this you should know, from NCERT only. See, metallic character, if you will move from top to bottom, always remember very few lines I am telling you. Metallic character, if you will move from top to bottom, it is going to increase. And if you are moving from left direction to the right direction in periodic table, now I have shown you the periodic table. If you are moving from this direction towards this direction, that means from S block towards P block, metallic character will decrease. It will decrease. That means non-metallic character will increase. That means S block elements are metals, P block elements are non-metals. Clear? Non-metals. See, metal comprises more than 78% of all the non-elements and appear on the left side of the periodic table. That is S block element. Now, metals are usually solid at room temperature, but there is an exception. Mercury is an exception. Gallium and cesium basically have low melting point. Also, this is also an exception. But the rest of them have high melting and boiling point. Okay, the next part. They are good conductor of heat and electricity. They are malleable, they are ductile. That means they can be beaten into thin sheets and the thin wires. Clear? Let us talk about non-metals. Non-metals are located at the top right hand side. That means the P block elements. That means which block? P block elements. Now, in fact, in a horizontal row, the property of element change from metallic on the left to non-metallic on the right. I already told you, metals on the left hand direction, non-metals on the right hand side. Now, non-metals are usually solid or gas, and they have low melting and boiling point. They had high, but there was an exception. They had low, but there are also an exception. That is the boron and carbon, which have basically high value. They are poor conductor of heat and electricity. They were good. Now, most non-metallic solids are brittle and are neither malleable nor ductile. Let us talk about now metalloids. The elements become more metallic as we go down a group. Metallic character will increase down a group. Across a period, it will decrease. Yeah. The non-metallic character increases as we go from left to right. Non-metallic will increase, metallic will decrease, right? Now, the change from metallic to non-metallic character is not abrupt as shown by the thick zigzag line. Now, the elements such as silicon, germanium, arsenic, antimony, tellurium, even polonium, students, these are metalloids, which shows the characteristic of both metals and non-metals. So, these are what, ma'am? These are metalloids. These elements are metalloids, which exhibits both the characteristics of metals as well as of non-metals. Now, students, we are going to start with the periodic properties section. First of all, I want you all to write it down so that we can start with the periodic properties, that is atomic radii, ionization enthalpy, electron gain enthalpy, and the last one, electronegativity. And then will be chemical properties. So, everybody first of all mark and write down these elements. These are again from the NCERT highlights. Now, we are going to start with the atomic radii, students. Give me a minute. So, students, I guess now you all have written about metals, non-metals and metalloids, right? Now, we are going to start with the periodic properties. Now, this is really very important, students. Let us understand this in depth. See, when I am talking about periodic properties, I will be talking about atomic radii, I will be talking about ionization enthalpy, about electron affinity and about electronegativity. So, starting with atomic radii, students, what do you feel is atomic radii? Atomic radius or atomic radii is the distance from the center, that means from the nucleus to the outermost shell. Now, to the outermost shell, electron, the valence electron. Valence electron is the electron that is present in the outermost shell, no? So, from distance from the center to the outermost shell is the radius. Now, we just not only have to understand about atomic radii, but we also have to understand about its trends, students. So, starting with the very first part, that what is about atomic radii? See, atomic radii, the trend they have given you, that when you are moving from left hand side to the right hand side in the periodic table, or you are moving from top to bottom. Let me show you once the periodic table, once and all. You will get an idea about it in detail, right, students? So, let us see about once the periodic table. This is your periodic table, my dear students. Let me just show you in a bigger section. This is your periodic table, the complete periodic table. And over here, students, when I will be again and again saying a term from left to right, you are starting from this direction towards this direction. This is from left to right. When you are saying, ma'am, from top to bottom, that means from this is your top and this is your bottom, from top to bottom. So, again and again these words will be, you will be listening to these words from left hand side to the right hand side, from top hand side to the bottom side. So, I guess now you know the term as well, right? Coming back to my thing over here about periodic properties, starting with atomic radii, I have already told you there are different kinds of atomic radii. Okay, but yes, this line we will understand in few more minutes. First of all, let us start with types of atomic radius. But before that, let me show you with the help of an diagram. If this is your nucleus, let us consider this is your first shell, your second shell, and second shell contains one electron. So, what is atomic radii? Distance from the center to the outermost electron is atomic radius or atomic radii. Now, if I'll talk about the types of atomic radius or atomic radii, the very first type we shall be talking about will be covalent radius. Now, what is covalent radius, ma'am? In covalent radius, we see that covalent bonding takes place. What happens over here, ma'am? Over here, ma'am, covalent bonding takes place. Now, how covalent bonding occur? Our question is, how does covalent bonding occur, ma'am? Covalent bonding occurs by the formation of covalent bond. Now, in covalent bond, there is sharing of sharing of electrons, students. So where there is sharing of electrons, there is covalent bond formation, and over there is covalent radius observed. Now see, let us consider this is atom first, atom second. They are sharing their electrons, so this is the overlapping region. Hence, when they are sharing their electrons, it is forming covalent bond. Clear, everybody? Now coming back over here again, how to calculate covalent radius? See, covalent radius, it will be observed. It will be observed in those cases which has basically difference in electronegativity. Which has a difference in electronegativity, in those cases we are going to observe the covalent radius or the covalent radii. Yes. Now how to calculate it? It's very simple. What you have to do, you have to add the radius of both of them divided by 2. For example, if you have A atom with you, let us consider we have similar atoms, then radius of A plus radius of another A, that means RA divided by 2. Radius of AA and the radius of another one, you have to add it, divided by 2 will come out to be the new radius for the covalent one. And for the different atoms, let us say A and B, you have to add radius of A plus radius of B plus 0.09, then comes into the electronegativity difference. Yeah, so in this basically we have to more focus upon the trends, not upon the radius types, but yes, you should know about it. It is 1/2 of the distance between the center of the two nuclei. So if you are connecting them and then you are dividing it by 2, this is basically your radius. This is basically your covalent radius. Yes. Now let us talk about the other type, that is van der Waals radius. Van der Waals radius basically is the largest radius. Basically it has the highest value or the largest value in size if I'll talk about. In van der Waals, basically it occurs in the case of molecules, though how it occurs, you can see it is distance from their radius divided by 2 is van der Waals 1, right? So it is also the weak bond, van der Waals bond, we say that it is the weak bond, right? So it is 1/2 of the internuclear distance between two adjacent atoms in two nearest neighboring molecule of the substance in solid state as shown in the figure. See, if I have to compare van der Waals and covalent, you can clearly see the distance is larger in comparison to covalent. In covalent, they were sharing, but in van der Waals, it is like this, right? So, van der Waals radii is more than covalent, hence we can clearly see. Also, students, van der Waals radius is seen in the case of inert gases. Very, very important key concept. Now moving on to the further one, we have metallic radii, which we are going to see in the solid state chapter. Over here, students, metallic bonding occurs. Over here, what happens, ma'am? Metallic bonding occurs. Now metallic bonding basically occurs between kernels and free electrons. Between whom, ma'am? Between kernels and free electrons, metallic bonding takes place. Right. Now over here in metallic bonding, the atoms are quite close to each other. So if I have to compare all of them all together, see covalent, this is covalent one in which we see the sharing. This is metallic one and this is going to be the van der Waals one. So distance from their nuclei divided by 2. Distance from their nuclei divided by 2. Distance from their nuclei divided by 2. Now this comes out to be what? Your radii respectively. So this is basically your covalent one. This is your metallic radii. And this is your van der Waals radii, which is largest. Van der Waals radius is largest, then comes metallic and then comes covalent. You can clearly see from the picture itself. Yes, everyone, do remember this because in the trend section also you are going to see this again and again. Now coming back over here, we are going to start with the periodic properties, students. We are going to start with the periodic properties. So I am going to tell you more about atomic radii. Let us see first of all. See, let us see the trend of atomic radii and on what factors does the atomic radii depends. Let us say the factors first of all. So the very first factor, students, that I shall be talking about will be nuclear charge. Will be what? Nuclear charge. What exactly is nuclear charge? Anybody, can you think about it? Nuclear charge is that charge which is exhibited by the nucleus on the outermost shell electron. Now, nucleus is a positively charged species. It will attract a negatively charged species towards itself. So, the charge exhibited by the nucleus on the outermost shell electron is nuclear charge. Charge by nucleus. Nucleus is positive in nature due to protons. So, the charge exhibited by them is basically our nuclear charge. Let us say that Let us consider that if you're increasing nuclear charge, that means nucleus is, attracting electron towards itself. Outermost, if outermost electron comes inside, size will decrease. So more the nuclear charge, lesser the size. So we can say if nuclear charge increases, students, size is going to decrease. Do remember this thing, right? Right, everybody? If size decreases, that means we are saying atomic radii decreases. Getting my point, everybody? That's great. Okay, let us talk about the second factor, that is going to be screening effect. Screening effect, in other terms, is also referred to as shielding effect. Now, what is screening effect or shielding effect? Let us consider. See, for example, we know this is your nucleus, this is your first shell, your second shell, your third shell. Let us consider there is one electron over here, right? And there are some electrons over here also. 1, 2, 3, 4, 5, 6, 7, 8. Here are 2 electrons. Now, what happens? See, this nucleus is exhibiting some force on the electron to come inside. But what will these inner electrons do? The inner electrons are going to repel. The inner electrons will repel. These electrons will repel. So there will be a repulsion between electron and electron, so that outermost electron cannot come inside. So what are the inner electrons going to do? They are going to create a shield over there with nuclei so that it cannot come inside. Now what happens? Let us take a case of the class, okay? If you are sitting in the class and you are favorite of your teacher, now you are sitting on the first bench and there is a student which is a backbencher and is creating so much mess. See, backbenchers do study a lot, I know that, but yes, there are some people, who are so irritating and they just don't want to study, they just irritate the class. So let us take an example that one of the backbencher is creating a mess, and so what teachers does? Teachers say, stand up and come over here, and teacher says to his favorite student that please go back because I have to pay more attention to that student because he's not paying attention. Now what happened is, for example, let us consider the initial student who was an intelligent one was like, no, I should have, if I'll go back I won't be able to understand. So what he does is he says that, ma'am, my head is paining, I won't be able to see from the last bench. Yeah, so what will happen? He's creating a shield so that he would not leave that position which is close to nucleus. Okay, so he's creating a shield so that the last electron cannot enter into the second one. So this is shielding effect. This is screening effect. Yes, everybody, this is also referred to as Z effective. Right? Now let us talk about screening power. Always remember, S has the highest screening power, then P, then D, and then F. This is going to be the screening power. Yes, students, yes. So if I talk about the basic trend from left hand side to the right hand side in a period, from left hand side to the right hand side in a period, just understand, in a period number will remain same. That means nuclear charge will increase. Why? Because atomic number increases. Nuclear charge is due to protons. Atomic number for a neutral molecule is equal to number of protons. So if you are moving from left to right direction, students, always remember that nuclear charge basically increases. If nuclear charge is increasing, size will decrease. That means atomic radii will decrease. So that means when you are moving from left hand side to the right hand side, atomic radii will decrease. Let us talk from top to bottom now. Now see, one more factor you can add over here, that is number of shells. See, shells are what? Shells are basically the value of n, the period number. For example, this is first shell. Let us take a case in which we have 1, 2 shell. Let us take a 3. So when you are moving from top to bottom, number of shells increases. What happened, ma'am? Number of shells increases. If number of shells are increasing, the distance of the nucleus and the outermost electron will increase. So atomic size will also increase. So from top to bottom, atomic size increases, and from left to right, it is going to decrease. Clear, everybody? Clear, everybody? Let us take few examples. Let us take few examples. Now talking about period number 2. See, in period number 2, you have to see lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon. See, now students, I have already told you, when you are moving from left direction to the right direction, what is going to happen? Ma'am, while moving, nuclear charge increases. So, atomic radius will decrease. Very simple. If atomic radius decreases, this is going to be the order. Yes, this is going to be the order. But ma'am, but, we know that neon is an inert gas, and inert gas basically exhibits which kind of radii? The van der Waal one. So van der Waal will be the highest, so it will come over here. So this is an exception. Highest will be of neon, then of lithium, then beryllium, then boron, then carbon, nitrogen, oxygen, fluorine. So this is going to be the order for period number 2. Clear everybody? Clear everybody? That's great. You can pause the video and write by your own, okay? Now let us talk about group number 1 and group number 2. See, if I'll talk about group number 1 and group number 2, it's very simple. Let us take group number 1. This is group number 1. Hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. See, when you are moving from top to bottom, ma'am, number of shells are increasing. So, atomic radii will increase. That means this is going to be the order for atomic radii. Clear? Clear everybody? Yes, everybody. Clear, 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 clear. So, for all the groups, you can clearly see. Now, group number 13 also, when you are moving from top to bottom, number of shell increases, so that the same atomic radii will increase. Now comes an exception, period number 3. Now, see, in period number 3, what happens? There is a different trend. See, you basically know that when you are moving from left hand side to the right hand side, nuclear charge will increase and atomic radius will decrease because they are inversely proportional, no? Atomic radius will decrease. That means this is going to be the order. This is going to be the order, but this is incorrect. Why, ma'am? Why? Let us write the configuration of all of them. See, this, its atomic number is 21, 22, 23, 24, 25, 26, 27, 28, 29 and 30. Let us write the configuration. See, over here what it is going to be? 4s2 3d1. Over here it is 4s2 3d2. Over here it is 4s2 3d3. Over here in chromium it is an exceptional electronic configuration 4s1 3d5. For Mn it is 4s2 3d5. For Fe it is 4s2 3d6. For cobalt it is 4s2 3d7. For nickel it is 4s2 3d8. Now for Cu it is 4s1 3d10, again an exception, and for Zn it is 4s2 3d10. Now see students, what happens? See, when you are moving from scandium, tin, manganese, the same concept will occur. What will happen, ma'am? Nuclear charge will increase and the size will decrease. This factor dominates over here. That means scandium will have highest, then titanium, then vanadium, chromium and manganese. But after this, if you are going to observe, see till now in 3d1, there are 5d orbitals, no? There is 1 electron. Here it is 2, here it is 3, here it is 5, 5. 5, here 5 refers to as that one orbital contains 1 electron. But as you are moving in this case, 6, 7 and 8, you see that electronic repulsion will participate. Here electron repulsion and nuclear charge, both factor will be seen. How? Let us see 3d6. So 1, 2, 3, 4, 5 and 6. So electron repulsion now occurs over here, right? So over here from Fe to nickel, what will happen? Electron repulsion occurs. Also, nuclear charge factor is also there. So they occur all together. If they are occurring all together, you know, after this what will happen? Fe, Co and nickel will have equal atomic radii. And after this, students, from nickel to Zn, what will happen here? Electron repulsion will be more. Why will be more? Because here it is 8 electrons, here it is 10, 10. If you are going to fill this 3d8, it is 1, 2, 3, 4, 5, 6, 7 and 8. Electron repulsion occurs over here. Now when there is an electron repulsion, nucleus will, if nucleus is over here and inner electrons are repelling the outermost, electron will go apart, size will increase. So what will happen? Due to electron repulsion, now size increases. So this is going to be the order for period number 3. Everybody please write it down. Yes, everyone, please write it down so that we can move on to the next part. Now students, comes the next exception over here. Yeah. Now this is for D block elements. This is your 3D series, your 4D series, your 5D series. If you remember, this is lanthanum and after them we have HF. So this is 57th atomic number. Now from 57 to elements. Some elements are there which are present in lanthanoid series after this. And after that we have hafnium. So basically over here if I'll talk about, again from top to bottom you will say that ma'am, number of shells are increasing, so size is going to decrease. So that means this is going to be the order, this is going to be the order, this is going to be the order. See, till over here lanthanoid series has not yet started, but in these cases after this lanthanoid series were there and after this we have hafnium and tantalum, no? So over here you will see that they will have equal atomic radii. Zirconium, hafnium, niobium and tantalum, they will have equal atomic radii. Why? Due to lanthanoid contraction. Due to lanthanoid contraction, this is going to be the order. Not for this one, but for these one, right? Due to lanthanoid contraction. Clear everybody? Shall I move on to the next one if it is done? Shall we move on to the next one if it is done, students? Yes. Now, as I was explaining you about the group 1 and group 2, I already told you. Now, there is one more exception, group number 13 to 18. So, let us take group number 13. Boron, aluminium, gallium, indium and thallium. See, in group number 1 and 2, I told you directly from top to bottom, number of shell increases, size increases. Here also, the same concept will occur, but there is an exception. See, number of shells, if they are increasing, size is going to decrease. Sorry. Size will also increase if number of shells are increasing. If number of shells are increasing, here also please kindly correct it. By chance I wrote it. If shells are increasing, the distance from the center to the nucleus will increase. So yes, it should increase. So if it is increasing, then only I have used this symbols. No, it is increasing. That means this should be the symbols. In the same way, I put the symbols correct, but I wrote directly size decreases. Kindly pardon me for that. See, come over here. Now, if size increasing, this should be the order. But over here, now the trend is quite different. See how the trend is quite different. I'll correct it. This is aluminium. This is gallium. Then we have indium. Here is thallium. See. Now, there is an exception that aluminium and gallium will have almost equal. Indium and thallium will have almost equal. See, students, now what happened? In aluminium and gallium, here, D block contraction occurs and over here lanthanoid contraction takes place. Now why this happen? See students, we know that S has good screening, then P, then D and then F. D orbital has poor shielding or poor screening effect. If it is poor screening, that means the orbitals are not protecting the inner electrons. That means what will happen? If they are not protecting the inner electrons, if they are not protecting it, electron will come inside, size will decrease. So size will decrease. So with poor screening, size will decrease. And let us say if something has a good screening effect or a good shielding constant, if a good shield is there at the nucleus, electron will go apart, repulsion will occur, size will increase. So over here, due to the presence of d orbital, there will be poor shielding, due to which it won't be able to protect it and electron will come inside and hence size will decrease. This was all about atomic radii, students. There are few more concepts about ionic radii if you want to see. Basically, they are saying that Pauling's empirical formula for ionic radii, that ionic radii is directly proportional to, now see here students, you have to just generally see that more the negative charge, more will be the ionic radii. More the negative charge, more the ionic radii. Yeah. So now, a cation is smaller than its parent atom while anion is bigger than its parent atom. Always remember that cation will have the smallest size, anion will have the largest. That's why I told you more the negative, more will be the atomic radii. Next. Among isoelectronic species, what are isoelectronic species? Which have same electrons. Cation with the greater positive charge will have a smaller radii. I told you, no, the one which has a negative charge will have a higher radii, the one with a positive charge will have a lower radii. So over here, cation which has a positive charge will have a smaller radii and anion with a greater negative charge will have a larger radii. Clear everybody? Clear? Now students, we are going to start with the next periodic properties of R, that is going to be ionization energy. What basically is an ionization energy? Let us take an example for atom. If this is nucleus, this is first shell, second shell. See, if there is an electron and I have to remove this outermost shell electron, the energy needed in order to remove this outermost shell electron is ionization energy. So, or the energy provided to remove this electron from the outermost shell is ionization energy. So, this is what is amount of energy required to remove the most loosely bonded electron from an isolated gaseous atom to form a cation. Now, how cation is formed? See, if I am a neutral molecule, I have positive and negative. If negative goes apart, I will be positive, I will be a cation. So, amount of energy required to remove an electron from the outermost shell is ionization energy. If an atom is exactly half filled or fully filled, electronic configuration, it has extra stability. Why it has extra stability? Because see, in fully filled configuration, let us say we have p orbital completely filled. Now, I am saying you have to give energy to remove an electron. You have to give a lot of energy. Why? Because it is stable. And from stable configuration, you have to provide a lot of energy to remove electron. That means fully filled will have the highest ionization energy, then will be half filled, and at last it will be partially filled. Yes, everybody, shall we see the factors for the ionization enthalpy? Okay, that's great. Now comes the factors session. See, in the case of factors, first is size of an atom. See, very simple, very simple. In general, I will give you a quick recap. In general, what you have to see from left to right. See, nuclear charge increases. Okay, size decreases. Always remember that ionization enthalpy is inversely proportional to size. Okay, electron affinity is inversely proportional to size. Electronegativity is inversely proportional to size. This is in general I am talking about, right? So, if size decreases, now ionization energy will increase. Electron affinity will increase. Electronegativity will increase. Getting my point? Clear, everyone? Now, see. From top to bottom, if I'll talk about, from top to bottom, if I'll say, ma'am, number of shells are increasing, so size increases. Size and ionization enthalpy are inversely proportional. Ionization enthalpy will decrease, electronegativity will decrease, electron affinity will decrease. This is the order. Now see, you know the answer, right? This is the general trend I've told you. Now let us see the factor. Ionization energy decreases with increase in atomic size, inversely proportional. Nuclear charge. See, more the nuclear charge, lesser will be size, more will be ionization enthalpy. That means ionization enthalpy is directly proportional to nuclear charge. If you are increasing nuclear charge, ionization enthalpy will increase. Clear? Now the next part is shielding or screening effect. Very simple thing. See, if it is poor shielding, that means they are not able to protect the electron. Electron will come inside, size will decrease. If size will increase, ionization enthalpy will increase. That means for poor shielding, ionization enthalpy is more. Now, for good shielding, what will happen, student? If it is good shielding, electron-electron repulsion will occur, size will increase, ionization enthalpy will decrease. Clear? Now comes penetration effect. So, always remember S has highest, then P, then D, then F. Yeah, this is for penetrating power. D has poor shielding, size decreases, ionization enthalpy will increase. They are correlated with each other. Next is electronic configuration. Already told you, fully filled will have highest, then half filled, and then comes the partially filled. Now let us talk about the trend, as I have already discussed with the trend, but yes, we have to take some examples. So we are taking example again of period number 2. Now see, in period number 2, it is lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine and neon. See students, over here you need to understand that what is going to happen when you are moving from this direction to this direction. Ma'am, nuclear charge increases, size decreases, ionization enthalpy will increase. This should be the order, but it is not. Ma'am, why? Ma'am, why it is not? Let us write the electronic configurations. First of all, write the atomic number 3, 4, 5, 6, 7, 8, 9, 10. Let us write electronic configuration 1s2, 2s1, 1s2, 2s2. Now, 1s2, 2s2, 2p1. For this, 2s2, 2p2. For this, I am writing for outermost 2p3. For this, 2s2, 2p4. For this, 2s2, 2p5. For this, 2s2, 2p6. I told you that fully filled will have the highest. Which of the following are fully filled electronic configuration? Ma'am, neon and beryllium. It has 2s2 complete, it has 2p6 complete. So these are the fully filled. They will have the highest. Ma'am, that means neon will have highest, and after neon it will be beryllium. After neon it will be beryllium. Or not? No ma'am, it doesn't go like this. It doesn't go like this. What will be seen? Just everybody first of all write it down. I'll let you know what will be seen over here. See, it's quite simple. Here you don't have to write neon, then beryllium, then boron. No. See students, just see. Here we know that neon will have highest. We know beryllium shows fully filled. And here if you see nitrogen, it is 2p3. 1, 2 and 3. It is half filled. It is also stable. So they will have their configurations. One, initially they will have more than the initial atom. If boron is present, it will have more than boron. If oxygen is present, it will be more than oxygen. So what is going to be the order? Lithium, then boron, then beryllium, then carbon, then oxygen, then nitrogen, then fluorine and then neon. This is going to be the order. Clear everybody? This is going to be the order for our configuration. Everybody please write down. This is going to be the order. Clear? Clear, 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 clear everybody. Clear, clear, clear. Done. Okay, now let us talk about the next one. Let us talk about the group number 13th. See, in group number 13th, what are you going to observe? This is a pattern W by which way you can learn it. This is something like this, okay? Yeah. So here it is boron, aluminium, gallium, indium, thallium. So this is the order. Boron will have the highest, then will be gallium, then if you're going to see thallium, then will be aluminium and at last it will be indium. This is going to be the order. Right? And if I'll talk about group number 1 and 2, so it is hydrogen, lithium, sodium, potassium, rubidium, cesium. From top to bottom, ma'am, we know that number of shells increases. So size will also increase. If size is increasing, ionization enthalpy will decrease. So if it is decreasing, this is going to be the order. Hydrogen will have the highest, then lithium, then sodium, then potassium, then rubidium, then cesium. Clear everybody? Everybody please write it down so that we can start with our next part. Shall we start with the next part now, students? Now, students, we are going to start with electronegativity and then I will be proceeding towards electron gain enthalpy. What is electronegativity? Electronegativity is tendency to attract shared pair of electrons towards itself. This is what is electronegativity. The trend is very simple. There is no exception over here. That means if you are moving from left direction to the right direction, left direction to the right direction, remember nuclear charge increases, size will decrease. Size will decrease, electronegativity will increase. Now only I told you electronegativity is inversely proportional. So it was basically it will increase. Now from top to bottom. From top to bottom, if I'll say number of shells increases, size will increase, electronegativity will decrease. So if I'll ask you the most electronegative element among the whole periodic table, that is going to be fluorine, people. Clear everyone? Now this was about electronegativity. Let us talk about the last topic, that is electron affinity, right? Or the electron gain enthalpy. What is electron affinity or electron gain enthalpy? See, if I'll talk about electron affinity, the amount of energy you are providing to an electron, to add into the outermost shell is electron gain enthalpy. And the energy that is basically absorbed and released at that spot of time. See, let me explain you again. If you are adding one electron into the outermost shell and the amount of energy you are providing it to enter into the outermost shell is electron gain enthalpy. And the amount of energy released at that spot of time is electron affinity. They both are negative of each other. If one is positive, another one is negative. Clear? So the trend is quite same when you're moving from left direction towards the right direction. Left direction towards the right direction. Nuclear charge increases, size decreases, electron affinity will increase because they are inversely proportional. Trend is going to be same for electron gain enthalpy and electron affinity, just the values are if it is positive, it is negative, right? Now from top to bottom, see, if number of shells increases, size will increase, electron affinity will decrease. Very simple topic. Now see students, there is an exception over here that fully filled, half filled, they will have 0 electron affinity. Why? Because you have to add 1 electron into the outermost shell, and in fully filled, if it is already filled, how will you add, right? So this is 0 for the for the ones that have the fully filled and the half filled one. Right everybody? Right. So there is one homework question, that is write the order for period number second for electron affinity. No need to worry students, in the next class before chemical bonding, I will give you its order as well. But I want you all to try once. Fully filled and half filled will have 0 value. Now you have to do it by own. I have given you a hint. The general order is given over here. Now let us talk about group number 1 and 2. Group number 1 and 2 will hold the same thing which is written over here. Number of shell increases, size increases, electron affinity decreases, right? But in group number 13th, 14th, 15th, 17th, and 18th, the order follows the same. Which order? See, let us talk in group number 13th. Boron, aluminium, gallium, indium, thallium. See, as you move from top to bottom, you are saying size basically increases. So, electron affinity should decrease. That means boron should have highest, then aluminium, then indium, then thallium. But this is incorrect. The second element will have highest than the first one. So, order will be aluminium will have highest, then boron, then gallium, then indium, then thallium. Similarly, in the case of carbon family, silicon will have more than carbon. Similarly, in the case of nitrogen family, the 15th family, what it will be? Phosphorus will have the highest. Right? Yes. Then arsenic, then antimony, then bismuth. Sorry, after phosphorus, it will be nitrogen. Second will have highest than the first one. And then the third, fourth, fifth. Similarly, second, first, third, fourth, fifth one. But in the case of group number 17, if I'll talk about fluorine, chlorine, bromine, iodine, right? I'm saying it should be like this. It should basically, size increases, it should decrease. But second will have highest. So what will be the order? Chlorine will have highest, then fluorine, then bromine, then iodine. One more thing, as I'm saying from, left to right, you are saying that size decreases, electron affinity increases. So now question that is asked again and again, which element is the one which has highest electron affinity among the whole periodic table? That is chlorine. Now comes for group number oxygen. The oxygen family 16th, it is quite different. See, oxygen, sulfur, selenium, tellurium and polonium. In this case also the order should be like this, but oxygen should have less than sulfur, no? Sulfur should be more, but in this case it is a different exception. Oxygen will have the least. It will be sulfur, selenium, tellurium and then polonium and at last oxygen. So this case is quite different. In this case, second atom will have more than first one, but over here first will have the least. First will have the least. Clear? These are the exceptions for electron affinity. Homework I have already told you students. Now comes our chemical properties. So in chemical properties, one of the chemical properties oxidation state or valency. Let us talk about oxidation state. Oxidation state, students, is basically the formal charge on any atom that an atom carries, and valency basically is the combining capacity of any element. So these two are different terms, not the same term, but yes, the different terms. So how do you calculate the valency of a respective element? You can easily calculate by the number of electrons in the outermost shell, or how you can calculate by subtracting from 8. 8 minus number of outermost shell, you will get the valency of that particular molecule. Now there is a diagonal relationship that is observed. The diagonal relationship is seen in in period number 2 and period number 3, right? In period number 2 and period number 3, you will see diagonal relationship. Diagonal elements will have same properties, right? So this is what is written. Some elements of certain group of second period resemble much in the period with the element of second and third period are diagonally related in properties, physical and chemical properties. So they exhibit diagonal relationship. Let us see how. See, on moving down the group, atom and the ion size increases down the group because shell increases. Next, when you are moving from left to right direction, across a period nuclear charge increases, size will decrease, right? But on moving diagonally, students, size will be same. When you are seeing diagonally, the elements, size will be same. In the case of period 2 and period 3, which element I will let you know. See, diagonal similarity. Now these are the reason why it is seen. See, what are the things that we observe? Diagonal similarity in electronegativity value. You will see similarity in electronegativity. See, now beryllium and aluminium, they show diagonal relationship. Yes, they show diagonal relationship. Now, why they show diagonal relationship? See, they don't have their sizes equal, but yes, their charge per unit area is equal. So they can also exhibit the diagonal relationship. Now there is also similarities between lithium and magnesium. They also exhibit diagonal relationship. See, this is your first group, this is second group. If you will see, lithium, magnesium are diagonal to each other, so they will have the same properties, right? Similarly, here will be group number, 13th. So, beryllium and aluminium, they will show the diagonal relationship. First group, second group, 13th group. So, I am showing you diagonal relationship between second period and the third period. See, what are the similarities? Lithium and magnesium both directly react with nitrogen to give the following compounds, but other alkali metals does not form nitrite. So, this is one similarity between lithium and magnesium. Another similarity, fluoride, carbonate and phosphate of lithium, magnesium are soluble in water, but other compounds of the alkali metals, basically they are insoluble in water, lithium and magnesium compounds, but another ones are soluble. Next, lithium, magnesium both are hard metals, but the other groups of the first A group family are soft in nature, right? So, they can show the relationship diagonally. More properties, their hydroxides are weak bases, while the hydroxide of the other group basically are strong base. They have high melting and boiling point. Next, when you are going to do the thermal disintegration, you are going to obtain these products. Clear? These are the similarities. Now students, here are the topic with regard to the oxides. Now oxides can be acidic, it can be basic, it can be amphoteric in nature. So they have discussed this over there, that elements on the extremely left hand side, if you are going to see of a period, basically that is the most basic one, whereas that they are formed on the extremely right one are the most acidic in nature. Yes. Now, amphoteric oxides are those which act as both acid and base, while neutral oxide are those which neither act as an acid nor act as a base. Examples are given to you. These are the lines from NCERT, students. These are the lines taken from NCERT. So now students, this end our today's session over here. I hope so that this one shot session, a quick revision section, ultimate recap session of this chapter, classification of elements and periodic properties, is clear to you. I have tried to complete each and every topic in detail, students. As you will know, it is ultimate recap. So we have to do quick revision, but though I have given you exceptions in detail, now do solve your homework questions. We shall be meeting in the next chapter, that is going to be chemical bonding, very soon. Thank you so much, my dear students. Have a good day. Keep smiling, keep learning. Thank you, students.